Mm-hmm.
So all 41 published chapters in this computational methods and data engineering volume went through a really rigorous peer review process.
Oh, okay.
Yeah, each paper was evaluated by 3 expert reviewers. These were drawn from a scientific committee, external reviewers, and the editorial board. So you have multiple layers of scrutiny there.
Got it. 3 sets of eyes.
At least. And the selection criteria were stringent. They prioritized papers that showed clear originality, significant impact, and exceptional clarity. So this multi-layered review process really ensures that what we're discussing today represents genuinely high-quality, impactful research.
And it certainly paints a picture of a massive, collaborative academic effort.
It absolutely does. The preface of the book actually extends its gratitude to the School of Computer Science and Engineering at Vellore Institute of Technology in India.
VIT.
Yeah, VIT, for their vital support in organizing the underlying conference. And they also acknowledge all the authors, presenters, and delegates for their invaluable contributions. It really underscores a broad community effort that brings such comprehensive research to light.
So let's maybe pull back the curtain a bit on the brilliant minds who curated this collection.
Mm-hmm.
I think understanding the editors' backgrounds can give us some unique insight into the breadth of expertise that shaped this volume. Who are some of the key figures?
Yeah, definitely. We have a truly stellar lineup here. Includes people like Dr. Vijay Kesari, Dr. Vijendra Singh, and Professor R.B. Patel. Each one brings a distinct and, frankly, impressive set of skills to the table. It really reflects the interdisciplinary nature of the field today.
Okay, let's start with Dr. Asari. What's his area of specialization? How does that shape the direction of these papers?
Right. Dr. Asari. He's a professor of electrical and computer engineering and holds an endowed chair in wide area surveillance at the University of Dayton.
Wow.
Yeah, and he directs their Vision Lab, which is a recognized center of excellence for computer vision and surveillance research. His prior role, founding director of the Computational Intelligence and Machine Vision Laboratory at Old Dominion University, further cements his expertise. He's really focused on how we analyze and interpret vast amounts of visual data using intelligent systems.
So very much the computer vision side.
Precisely. His focus clearly steers research towards how AI perceives and understands the visual world around us.
Okay. And Dr. Vijendra Singh, what deep expertise does he bring to the table?
Dr. Singh is a professor in the School of Computer Science at the University of Petroleum and Energy Studies in India. He brings, get this, 2 decades of extensive experience in both research and teaching.
20 years?
Yeah, including time in the IT industry as well. His primary research concentrations are really foundational to modern data science: data mining, image processing, big data, machine learning, and deep learning.
The core stuff.
The core stuff. He's published over 85 scientific papers in these areas and served in prominent editorial roles. His work is truly at the forefront of the core algorithmic advancements that power basically everything from data analysis to intelligent systems today.
That's an incredibly extensive publication record. Really showcases a profound impact. How about Professor R.B. Patel?
Professor Patel, he's a professor in the Department of Computer Science and Engineering at Chandigarh College of Engineering and Technology. He has a notable academic history, including leadership roles like Dean of the Faculty of Information Technology and Computer Science. His research areas are equally diverse and critical for today's connected world. They span mobile and distributed computing, machine and deep learning, and wireless sensor networks.
Wow, quite a range.
It is. And he has an even more impressive publication count, over 150 papers. Plus, he's guided 16 PhD scholars, with 2 more currently in progress. It really underscores his deep influence on the next generation of researchers in this space.
So, connecting the dots here.
Yeah.
The collective expertise of these editors, from computer vision and surveillance to data mining, big data, distributed computing, it truly provides a foundational understanding of just how interdisciplinary computational methods are today.
Absolutely.
This diversity is clearly reflected in the wide array of topics covered within these proceedings, wouldn't you say?
Couldn't agree more. Their combined knowledge and broad perspectives are precisely what allows this volume to touch upon so many different applications. It really highlights how modern computational methods inherently cross traditional disciplinary boundaries. You need that holistic understanding to push the field forward.
Okay, let's unpack this. With that foundational understanding of who's driving this field, where do we see these cutting-edge computational methods making the biggest splash? out there in the real world.
It's truly astonishing when you look at it, isn't it? These methods aren't just theoretical anymore. They are actively revolutionizing industries and, well, our daily lives.
Yeah.
Maybe start with how they're transforming how we interact with information and communication itself.
Good place to start.
Yeah.
Hashtag tag 2.1, revolutionizing information and communication. And a huge part of that has got to be natural language processing, NLP, the ability of computers to understand and process human language. I saw a fascinating paper in here on SME's text summarization. Why is that such a unique and significant challenge?
Yes, that's a perfect example of what we call a low-resource language problem.
Low resource.
Yeah, languages like Assamese present specific difficulties. You've got unique sentence structures, inflectional words, complex grammatical rules, and compounding this, there's often a severe lack of automated tools, very limited databases for understanding word meanings, ontological knowledge, and insufficient platforms for knowledge sharing.
So it's harder to build these tools from scratch.
Exactly. All these factors make deep NLP research for these languages particularly challenging, but it's also incredibly important for bridging digital divides,
That really highlights the complexity. And what was a surprising insight from this particular research on Assamese? Anything jump out?
There was a truly unique insight, actually. They found that nouns, just nouns as a part of speech, have a disproportionately direct impact on the relevancy of a sentence within a text.
Just nouns.
Just nouns. In fact, they found that with the inclusion of more nouns, the overall relevance of the sentence actually enhances.
Wow.
Yeah, so it means it's not just about complex algorithms all the time. Sometimes a simple linguistic element like a noun can hold significant power in determining meaning.
That's fascinating. So how did they propose to tackle this? They combined graph theory and noun counts, right? How did that work?
Right. Their novel solution integrates graph theory with this strategic counting of nouns in sentences. It progresses through three major phases.
Okay.
First is pre-processing. This involves standard steps like normalization, tokenization, breaking text into words, removing common stop words like the or a, and stemming, which reduces words to their root form.
Standard NLP prep.
Pretty standard. Next, they move to feature extraction, pulling out specific linguistic and statistical patterns. And finally, in the third phase, they apply a ranking method. They use the LexRank algorithm, computing a final score.
And that score is based on?
It's based on several factors. Things like TF-IDF, which measures word importance, sentence position, sentence length, identifying numerical and cue words, and crucially, the specific identification of nouns, all analyzed through a cosine similarity matrix to measure how similar sentences are to each other.
Okay, a combination of factors with nouns playing key role.
Precisely.
And what was the performance impact of this approach, especially with that focus on nouns? Did it work well?
The researchers emphasized that the use of nouns enhances the performance significantly. Their approach actually outperforms the latest graph-based text summarization approach in the Assamese language.
Wow, so a real improvement.
Yeah, it's a significant leap forward. It demonstrates how deeply understanding the nuances of a specific language can lead to breakthroughs, even for these low-resource languages.
Okay, shifting gears a bit to some of the more widely recognized language models. We also see the powerful application of BERT and GPT-2 for tasks like question answering and text generation.
Yes, the big ones?
What's the core motivation behind these specialized fields? They seem to be everywhere now.
They really are. These are specialized fields within information retrieval. They aim to automatically find answers to very specific questions like who, what, where, how. The goal is usually to provide the shortest, most precise answer possible.
Like a super smart search engine.
Kind of, yeah. Their potential applications are vast. Think automating customer service, moderating online forums like Stack Overflow or Reddit, or just providing immediate, concise info from large websites. They essentially act as highly intelligent digital librarians, retrieving or generating information on demand.
And the transformer architecture is absolutely central to both of these, right?
Mm-hmm.
Can you give us a simplified sense of how that works, without getting too deep in the weeds?
Sure, I'll try. Yes, the transformer architecture is key. It's designed to handle sequential data, like language, very efficiently. Basically, it consists of two main parts. An encoder, which processes the input text to understand its meaning and context.
Okay, the input part.
Right. And a decoder, which uses that understanding to generate new text or answers. The output part. They work together in tandem to learn complex patterns and relationships within language, much better than older methods could.
Let's delve into BERT first as the encoder part. How does it function, and what makes it so revolutionary for understanding context?
Okay, BERT. Bidirectional encoder representation from transformers. That's the encoder side. What makes it revolutionary is its bidirectional training approach.
A directional meaning.
Meaning, unlike older models that might read text only from left to right, BERT analyzes a text sequence from both left to right and right to left simultaneously.
Ah, I see. Both ways at once.
Exactly. This allows it to learn incredibly deep contextual information about each word by considering all the surrounding words. It achieves this through a clever technique called a masked language model during its pre-training phase, where it basically predicts missing words based on their full context.
Okay.
Then when you fine-tune it for something like question answering, it learns to pinpoint the exact start and end of an answer within a document, predicting that span with the highest probability. It really understands the context.
And then there's GPT-2, the generative powerhouse, acting as the decoder. What allows it to create such, well, remarkably human-like text?
GPT-2. Generative Pre-trained Transformer 2, that's the decoder part. It's truly massive in scale. Built with 1.5 billion parameters and trained on a huge data set, 8 million web pages.
Wow.
Its generative nature means it's specifically trained to predict the next word or token in a sequence. This seemingly simple task, when performed on such a vast amount of data, allows it to produce text that is remarkably coherent and fluent. It often generates long passages that are nearly indistinguishable from human writing.
It's like it learned the underlying rules of language.
In a way, yes. It's essentially learned the patterns and nuances of human language so well that it can continue a thought or a story with impressive accuracy.
That's incredible. But these sound computationally demanding. Is there any work on improving efficiency for these large models?
Absolutely. That's a big focus. The research highlights efforts to make these powerful models more practical. For instance, there's DistillBERT. It's a pre-trained version of BERT that's 60% faster and 40% smaller.
60% faster. That's huge.
It is. And despite its reduced size, it maintains strong language understanding capabilities, achieving an impressive 97% accuracy. So this shows a clear path towards more deployable and efficient large language models, less resource intensive.
Okay, beyond just generating text, these computational methods are also vital for tackling misinformation and online harassment. Those are pervasive issues today.
Hugely important, yes.
Let's talk about fake news detection in mainstream media using BERT. This feels like a critical challenge in our digital age, doesn't it?
It is, absolutely. The paper really underscores this critical problem of falsified information, fake news infiltrating platforms with large audiences. Think news channels, radio, even despite existing filtering efforts.
Right, it still gets through.
It does. This highlights the urgent need for robust automated detection mechanisms to, well, safeguard public discourse.
So what's the proposed solution using BERT for this real-time classification?
Right.
And what's innovative about how it handles different types of news input? It's not just text, is it?
No, and that's key. The researchers propose a relatively simple yet reliable solution for real-time fake news classification focused on mass media sources by leveraging BERT. What's particularly innovative is its versatility in handling various news inputs.
Like what?
Well, users can input news via speech to text. It uses Google's speech recognition engine to convert audio from live broadcasts, say on TV or radio, into text.
Indeed.
Or alternatively, they can use image OCR, optical character recognition, for images captured from TV news. Think headlines, scroll text at the bottom of the screen.
Okay.
This OCR method requires significant pre-processing, though. Steps like adjusting skewness, converting to grayscale, thresholding to enhance contrast, removing noise, all to ensure accurate text extraction using tools like Tesseract.
So it can read the screen, basically.
Essentially, yes.
And BERT's role, again, is about understanding context, right? How does that help detect fake news specifically?
Precisely. BERT is crucial because it establishes that contextual relationship between a key or token word and its adjoining words. This allows the model to understand if news is fake, not just by identifying specific problematic words, but by analyzing the broader context in which those words are used. It checks whether that context aligns with factual reporting or known misinformation patterns. It's about discerning the subtle linguistic cues of deceptive content, not just keywords.
And the performance results for this model, were they good?
They were very impressive, actually. The model achieved an accuracy of 96.5% on its test set for classifying news as real or fake.
96.5.
Yeah. It also boasted an F1 score of 0.9655 and an ROC AUC of 0.965. To put that in perspective, this significantly outperforms older methods like logistic regression, which only manage about 0.63 accuracy, or even random forest at 0.85. It's a substantial improvement in reliably detecting fake news.
Okay, another pervasive and damaging issue online: toxic comments and online harassment. How are computational methods, specifically extreme gradient boosting, addressing that?
Right. The paper on extreme gradient boosting for toxic comment classification really highlights this widespread problem. Offensive comments and abuse from malintent users. It's everywhere online.
Unfortunately, yes.
And this hostile environment often forces many people to withdraw from discussions or shut down essential conversations. It severely impairs the free exchange of ideas and, ultimately, harms the entire online ecosystem. It's a critical societal problem for digital platforms.
So a scalable and effective solution is clearly needed. They're using XGBoost here. What makes XGBoost particularly suitable for this kind of large-scale classification challenge?
XGBoost, or extreme gradient boosting, is introduced as a scalable method for effectively classifying toxic comments. It's chosen precisely because of its effectiveness, flexibility, and portability. The process involves thorough steps like corpus creation and text preprocessing.
The usual cleaning steps.
Yeah, converting text to lowercase, removing punctuation, common stop words, numbers, URLs, standardizing whitespace, all that. This is followed by creating a bag of words, BERT model, which basically represents text as a collection of its words, ignoring grammar but keeping the word counts.
Okay. What are XGBoost's specific technical advantages then? What makes it so powerful for this?
Its primary advantage lies in its use of gradient boosting. This is an iterative process where new decision trees are added in each step to progressively reduce the errors made by the previous trees.
So it learns from its mistakes, kind of.
Exactly. This sequential optimization helps the model learn very complex patterns in the data. Additionally, it incorporates strong regularization techniques. These are crucial for preventing overfitting.
Overfitting, meaning it doesn't just memorize the training data.
Right. It ensures the model learns generalized patterns rather than just memorizing the specific toxic comments it was trained on. This means it performs well on new, unseen comments out in the wild.
And what did the research find about the impact of scale on its performance? That seems important for platforms with millions of users.
Yeah, that's critical. The research clearly emphasizes that increasing the size of the training set by adding more comments results in better performance.
More data, better results.
Yeah.
Makes sense.
And crucially, they also found that using a larger vocabulary results in a dramatic improvement in the model performance. This really underscores XGBoost's inherent suitability for handling the vast and ever-growing datasets found on large social media platforms. It makes it a potentially powerful tool in the fight against online abuse.
Speaking of large platforms and online interactions, understanding the customer voice is absolutely crucial for businesses, especially in, say, the financial domain. How is natural language processing being used there to understand the often unspoken reasons and motivators behind customer calls?
Right. This paper addresses a really significant business challenge. Customers get unsatisfied if they have to call about something which they could have done online. We've all been there, right? And this makes incoming calls a high-cost component for financial institutions. So the core goal is to intelligently mine the reasons and motivators behind these calls. This allows companies to potentially improve their online services and reduce those costly call volumes.
And they propose an innovative dual-model approach to tackle this. Can you elaborate on how these two models work together? It sounds complex.
It's pretty sophisticated, yeah.
Yeah.
The first model focuses on reason extraction. It employs an advanced neural network, an attention-based stacked bidirectional long short-term memory network, followed by hierarchical clustering.
Okay, that's a mouthful. What does it do?
It is. Basically, this setup allows it to directly extract the core reasons from the call transcripts, generating concise summaries, short customer intents, or rep notes that capture why a customer called.
Got it. The why.
Exactly. The second model is for motivator classification. This uses a set of ensemble models, multiple models working together to categorize the underlying motivators driving those calls. This task is complex because the dataset is highly imbalanced. Meaning some reasons are far more common than others. For example, attempted to do something online but was unable to, accounted for 23% of calls in their data, while following up a communication was a tiny 1%. This imbalance makes classification tricky.
Right. The model might just focus on the common cases.
Precisely.
And it sounds like these ensemble models, combining different approaches, really made a difference here. especially with incorporating additional data sources.
They certainly did. That was a key finding. The ensemble models have outperformed the independent models specifically because they were able to capture information from different sources.
Like what kind of other sources?
Well, for instance, for that motivator attempted to do something online but was unable, they discovered that beyond just the call transcript features, other data like clickstream features, things like customer sessions on website, were a powerful signal.
Ah, so tracking their website activity too.
Exactly. And incorporating that clickstream data actually increased the prediction precision for that motivator by 30%.
30%, that's huge.
It is. It highlights a critical aha moment. Combining diverse data streams, called transcripts, website clicks with intelligent ensemble methods can unlock significantly deeper insights into why customers are contacting you. And here's where it gets really interesting. Beyond just words and communication, these computational methods are making a profound difference in, well, our personal health and daily well-being. Hashtag 2.2 AI for health and well-being.
That's a huge area of impact. Let's start with advancing medical diagnosis. Beginning with diabetes prediction. Why is early prediction of a condition like diabetes so critical, and what methods are proving most effective?
Right, diabetes. It's a chronic disease, currently no known cure. But early prediction is absolutely vital. It can help prevent any further complications, serious things like heart disease, nerve damage, liver damage. Getting ahead of the disease can significantly improve a patient's long-term health and quality of life.
Makes sense. Get treatment earlier.
Exactly. The study we're looking at utilized the Pima Indians diabetes dataset. It's a well-known benchmark in the field, comprises 768 patient instances, each with 8 features, things like glucose tolerance test results, body mass index, BMI, age, and so on.
Okay, a standard data set. And what machine learning algorithms did they test for prediction? Did any specific features stand out as particularly important?
They systematically tested several common classification algorithms. Support vector machine, SVM, naive Bayes, NB, random forest, RF, logistic regression, LR, K in nearest neighbor, KNN, and gradient boosting classifier, GBC.
A whole suite of them.
Yeah, a good comparison. They also found that plasma glucose level was the most informative feature for prediction, followed closely by mass, BMI, age, and insulin levels.
Okay, so glucose is key. Which of these models proved to be the outperformer then? And what does that tell us about its potential in, actual clinical settings?
The clear winner was random forest. The random forest prediction model outperforms all the other prediction models they tested, achieving an impressive accuracy of 96.67%.
Wow, nearly 97%.
Yeah. This was significantly higher than the next best, which was GBC at around 87.6% or KNN at about 86%. This striking performance really showcases the power of ensemble methods like random forest for this diagnostic task. It suggests it could be a highly reliable tool for early diabetes risk assessment, potentially leading to earlier intervention and better patient outcomes down the line.
Okay, moving from general health to dentistry. How is AI being used for orthopantomogram OPG image analysis? And classifying dental defects sounds like a big leap from just a dentist looking at an X-ray.
Indeed, it's a significant advancement. This paper proposes an AI-enabled system for the field of dentistry to analyze OPG images. OPGs are those common panoramic X-rays of the teeth and jaws.
Right, I've had those.
Most people have. The process here is quite streamlined. An input OPG image is fed into a machine learning model. Specifically, it uses faster RCNN, which is an object detection algorithm known as the bounding box.
Okay.
This model then generates a comprehensive diagnosis report, accurately outlining all the defects in a classified manner. Things like cavities, bone loss, infections, etc.
And how is the sensitive patient data from these reports managed? Security must be a big concern.
Absolutely. The system addresses this by utilizing Firebase Cloud Storage, which is developed by Google. This acts as a cloud-hosted database to store these reports in a more secure, accessible, and organized way. It helps ensure patient privacy and data integrity.
What about computational efficiency for this dental AI? Was faster RCNN chosen for a specific reason beyond just accuracy? Speed matters in a clinic?
That's a great point. Yes, faster RCNN was selected partly because it's more efficient in object detection and it's time efficient compared to some other convolutional neural networks, CNNs.
Okay.
It apparently improves accuracy without further techniques used, meaning it's robust without needing extra complex steps, and it can effectively classify the defective nature of the teeth. So its balance of speed and precision makes it seem ideal for practical clinical use where rapid diagnosis is important.
Okay, sticking with medical imaging but moving to the brain. Kidney stone detection using something called XResNet 50. What's the advantage there?
Right. This involves applying CNNs specifically for detecting kidney stones from CT scans. The paper introduces XResNet 50 as an improvement over the most commonly used ResNets.
ResNets are a type of CNN, right?
Exactly, a very successful family of them. The benefits of XResNet, according to the paper, are that it's less computationally expensive, and so training this model is easy. This comes from making some minor tweaks to the original ResNet architecture.
What kind of tweaks?
Things like adjustments to the regular ResNet architecture to improve the learning rate decay, mix-up training, label smoothing, and knowledge distillation. Small changes that add up to better performance and efficiency. They mention that the base ResNet 50 itself contains 48 convolutional layers, 1 max pooling layer, and 1 average pooling layer, so it's already quite deep. XResNet refines that structure.
Interesting. And for brain tumor detection, they used a neurofuzzy classifier. That sounds like a hybrid approach.
It is. This addresses the challenge of diagnosing brain tumors from MRI images, which requires high precision. They used a neurohuzzy system, sometimes called NFC or NEF class. It's essentially a rule-based expert system utilizing fuzzy rules.
Fuzzy rule.
Yeah, meaning rules that handle uncertainty and vagueness, which is common in medical diagnosis. It has 3 main components. It defines fuzzy input-output variables, computes their fuzzy values, and uses a set of fuzzy rules, fuzzy inference approach to make decisions.
And what are the key features of this NEF class system?
A key feature highlighted is its ability to incrementally learn the rules of fuzzy classification. And importantly, its learning approach does not affect the basic fuzzy classifier semantics, meaning it learns without breaking the underlying fuzzy logic structure.
What's the logic it uses underneath?
The paper mentions that the fuzzy ID3 algorithm is used in the classifier to build the decision trees. This algorithm aims for less uncertainty and capturing more information by using the fuzzy entropy measure.
Okay. And how do they evaluate its performance? What metrics do they look at?
They used a comprehensive set of metrics to demonstrate proficiency. Things like sensitivity, specification, accuracy, F-score, positive predictive values, PPV, negative predictive values, NPVs, false reject rate, FRR, and false accept rate, FAR. So a really thorough evaluation of its diagnostic capabilities.
Beyond physical ailments, the challenge of early Alzheimer's disease detection is also critical. How are machine learning techniques and EEG signals being leveraged for this incredibly difficult diagnostic task?
Yeah, diagnosing Alzheimer's, especially in the early stages, it is very difficult to diagnose the AD. Symptoms can be subtle, overlap with other conditions. It's tough for clinicians. The study highlights the innovative use of electroencephalogram, EEG, signals, which measure brain activity as a primary diagnostic input.
Okay, EEG.
Right. This is often combined with other brain imaging tests like CT scans, MRI, PT, SPECT, and even examining cerebrospinal fluid, CSF, to get a really comprehensive picture.
And what's the typical pipeline for processing these complex EEG signals? How do you get from raw brainwaves to a potential diagnosis?
It generally involves 4 main steps to transform that raw EEG data into actionable insights. First, pre-processing. Meticulously removing noise, artifacts from muscle movements or eye blinks, and apply filters.
Cleaning the signal.
Exactly. Second, feature extraction. This is where meaningful patterns and characteristics are derived from the clean signals. For example, using fast Fourier transform, FFT, to analyze power spectral density, PSD characteristics, or wavelet transforms, WT, both continuous and discrete forms to analyze non-stationary signals in the time-frequency domain, basically finding the important patterns.
Okay.
Third, feature selection. Choosing the most discriminative and relevant features identified in the previous step, which helps reduce complexity and improve model performance. And finally, classification. This is where various supervised learning algorithms are applied, specifically classification methods like support vector machine, decision trees, nearest neighbor, discriminant analysis, neural network. These algorithms learn to classify the signals, often indicating the presence or risk of Alzheimer's based on the patterns they detect.
Okay, so quite a sophisticated process. Beyond diagnosis, AI is also creating incredible assistive technologies that truly enhance daily living. Tell me about the walking assistants being developed for visually challenged persons. This sounds like a direct and powerful application.
It is a remarkable example of technology empowering individuals. The device described is specifically designed to monitor the surroundings and vocally explain the surroundings to a visually impaired person.
Like a verbal guide.
Exactly. Its mission is to help them navigate by prompting him using recorded voice messages, offering a sense of their environment that might otherwise be inaccessible. The output isn't just voice, though. It can also include a vibration motor and even a heat generator to convey different types of information non-verbally.
What were the critical design considerations for this device, especially regarding the sensing module, the eyes of the system?
A key consideration was the position of the sensing module. Where you place the cameras or sensors is crucial for ensuring its range and effectiveness.
Makes sense.
Yeah, improper placement could lead to a reduction in range, unstable images or obstructed view, or even damage to the module. And in an outdoor environment, any of those could have serious safety consequences for the user.
Definitely. And what core object detection algorithm powers this system? How does it identify obstacles and surroundings in real time?
They chose YOLO, which stands for You Only Look Once.
YOLO. Okay.
It's a state-of-the-art object detection algorithm that has proven particularly helpful for pedestrian environments. The reason for its selection is primarily its speed. It operates at 30 frames per second FPS, which is significantly faster than many counterparts that might run around 12 FPS.
And speed is critical for real-time navigation.
Absolutely. Remarkably, YOLO can even run on systems with no GPU. This greatly reduces hardware requirements, making the device potentially more accessible, lighter, and more power efficient. YOLO achieves this efficiency by dividing the image into a grid and assigning object probabilities to each grid cell, computationally saving resources by not processing empty areas as much.
Smart. And what future enhancements are planned for this device? It sounds like it has immense potential to evolve further.
Absolutely. They plan to address the current height restriction of 2 feet above ground. The goal is to enable the device to prompt about unevenness of the ground, detecting curbs, potholes, steps, which is a major safety concern.
Oh yeah, definitely.
They also intend to modify the output mode by using vibration signals instead of voice messages. This would make the device accessible and effective for visually impaired individuals who are also deaf, expanding its reach significantly.
That's fantastic. Finally, in this realm of well-being, how are computational methods supporting mental health in online spaces? That seems like a very complex and sensitive area, especially given interactions within social networks.
It is a truly fascinating and innovative application. The research begins with the scientific premise that the human mind behaves in accordance with the thoughts and subconscious mind, and that the subconscious stores all the information that the human perceives.
Okay, an interesting starting point.
Building on this, they introduce HappyOSN. It's a system developed to improve the mental health of the online social network, OSN person, by monitoring the activity log.
Monitoring activity. How does that translate into improving mental health? Can you walk me through the 4-step process of HappyOSN? It sounds quite sophisticated.
Certainly. The system operates in 4 innovative steps. First, it identifies the communication correlation within a user's online interactions, who they talk to, the patterns. Second, it continuously monitors the user's activity log, posts, comments, likes. It then uses PyTorch, a powerful machine learning framework, to text classify the topics, identifying the contents category, or, more importantly, its emotional tone.
Okay, so it's reading their posts and figuring out the sentiment.
Essentially, yes. Third, and this is the really novel part, if it detects a negative trend, it searches a subliminal repository for the corresponding content category and automatically posts it in their OSM page.
Wait, subliminal content, what does that mean here?
Yeah, it's intriguing. By subliminal content, they mean subtle cues or even potentially hidden frequencies embedded within audio or video content. It's designed to influence the subconscious mind, almost like a gentle, imperceptible nudge in a positive direction, perhaps without the user even consciously realizing it.
Wow, okay, that's different. And the 4th step?
The 4th step is monitoring. The emotion shift is monitored periodically to assess the impact of these subliminal interventions. Are they actually helping shift the user's emotional state in a positive direction?
What was the impact of HappyOSN on mental health metrics? Did it show tangible improvements according to the study?
According to the paper, yes. The recorded results showed significant improvement in all the considered metrics, things like accuracy, recall, and F1 score for detecting emotional shifts when compared to existing models. It represents a novel, perhaps slightly controversial, but promising approach to leveraging online activity and subtle interventions for proactive mental health support. It really showcases how AI can be applied to deeply personal and sensitive areas. So, what truly powers these incredibly diverse applications we've just discussed? Spanning communication, health, well-being. It's the computational powerhouse of the techniques themselves, really. Hashtag tag 2.3 engineering smarter systems.
And that includes building intelligent infrastructure. like smart street lamps. This tackles a pretty common urban problem, right? Energy waste.
Absolutely. Street lighting becomes an imperative component for road safety and crime prevention in urban environments. We need it. But conventional public street lamps consume more energy without the lack of energy-efficient management.
Lights on full blast all night. Nobody around.
Exactly. This leads to significant urban energy waste. Huge amounts of electricity just lighting up empty streets.
So how does this proposed smart street lamp system offer a solution? It uses fog computing, machine learning, and IoT. How does that all come together?
Right. The system implements an innovative energy-efficient management over fog servers. It works by automating the adjustment of luminance in streetlights, using IoT sensors and machine learning.
Fog servers. That means processing closer to the lamps.
Precisely. Instead of sending everything to a central cloud, some processing happens closer to the edge. The real genius here is how real-time detection of movement, pedestrians, vehicles facilitated by these IoT sensors and machine learning algorithms, magnifies the efficient power consumption.
So the lights react to movement.
Exactly. Specifically, they use the gradient boosting algorithm to recognize the patterns of activity and dynamically adjust the luminance of the lights, dimming them when no one is present, brightening them as vehicles or pedestrians approach.
What are the main benefits of this fog-enabled IoT framework? Is it just about saving energy, or is there more to it?
It provides multiple interconnected benefits. It obviously creates energy-conserving units. It enables efficient management in streetlights by tracking the states of street lamps, knowing if a bulb is out, for instance. This leads to reduced wastage of energy. But, critically, it also improves quality, accuracy, power consumption, and reduced latency in the urban lighting system. Makes them not just greener, but also more responsive and effective overall.
Okay, another groundbreaking area. Self-driving cars. We saw the AutoNav model for lane and object detection. What's the current state of autonomous vehicles generally? And why are they considered such a transformative advance in AI?
Autonomous vehicles, or AVs, they're definitely among the most groundbreaking advances in the area of artificial intelligence. The Society of Automotive Engineers, SAE, categorizes them from level 0, no automation, up to level 5, full automation, no driver needed ever.
And where are we now, commercially?
Commercially, we're primarily seeing level 1 to level 2 automation. Things like adaptive cruise control, lane keeping assist. They still require active driver engagement. Full self-driving is still mostly in development and testing.
Right. Why are they so important, though? What's the big promise?
Their importance is immense because they could significantly minimize risks. Studies show something like 94% of accidents are due to human behavior, distraction, error, impairment.
Wow, 94%?
Yeah. AVs promise to make roads much safer for pedestrians and other vehicles. They could even assist in managing parking problems, potentially freeing up to 48% of existing parking space through more efficient vehicle movement and self-parking.
Okay, that's a big potential impact. What are the key components that enable an AV to perceive and navigate its environment?
There are 5 main components that have to work together seamlessly. You've got perception, localization and mapping, path planning, decision-making, and vehicle control. This particular paper primarily focuses on perception.
The seeing part.
Exactly. The car's ability to see and interpret its surroundings. This utilizes various sensors, ultrasonic sensors, LiDAR, which uses lasers, radar, using radio waves, and traditional cameras, all scanning the environment in real time.
How is lane detection implemented in this AutoNav model? What techniques do they use, and what kind of accuracy did it achieve?
For lane detection, they rely on classic computer vision techniques combined with simulation. They use the canny edge detection algorithm to identify edges in the road markings, followed by the whole line transform to find the straight lines representing the lanes. They simulated this process in the CarLA simulator, which is a common tool for AV research. They also highlight the high accuracy of their dynamic region of interest selection algorithm, which was close to 99% accurate in identifying the relevant parts of the road for focusing the lane detection.
And for object detection, identifying other cars, pedestrians, obstacles, what method is used there?
For object detection, they utilized SSD MobNet 640x640 for training the model. This specific model was chosen for its good speed versus accuracy trade-off and its relative ease of training, making it practical for real-time applications in AVs. It's designed to quickly and accurately identify various objects in the car's path.
What were some of the crucial real-world challenges they discovered during testing? especially when they used larger data sets or simulated bad weather. This often highlights the gap between the lab and reality, right?
Absolutely. This is a critical insight into the complexities of deploying AI in the real world. While their initial precision for object detection was promising, around 75%, it actually dropped off to around 60% when tested with a much larger data set, about 500 images under bad weather conditions simulated in the simulator, specifically an overcast sky.
So performance dropped in bad weather. Why?
They attributed this performance drop to challenges like inconsistent labeling of certain objects in the larger data set, like poles, apparently, and also the significant effect of the absence of sun on the model's performance. Lighting conditions really matter. These findings underscore that real-world variability, weather, lighting, data quality are often the biggest hurdles, even for algorithms that perform well under ideal conditions.
Makes sense. How about the autonomous driving control aspect? Essentially, how the car decides to steer or accelerate based on all this perception data.
For the control aspect, they implemented behavioral cloning. They use a 5-layer convolutional neural network, CNN, for this. This was deployed in the Udacity simulator to make live predictions for vehicle control steering angle throttle.
Behavioral cloning. It learns by watching humans drive.
Basically, yes. It involves training a model to mimic human driving behavior by learning from recorded driving data. The goal is for the car to make decisions steering, acceleration, braking based on what a human driver would likely do in similar situations perceived by the sensors.
Okay, moving to optimizing resource management. Let's talk about agriculture. How is machine learning being used for sensing things like nitrogen and temperature? Using chlorophyll maps. Precision agriculture, right? Exactly, precision agriculture. It's a technique that uses spatial data linked to specific locations in a field to monitor things like the nutrient status of crop, overall vegetation health, soil health, and to help with management nutrient optimization initiatives.
So, tailoring treatment to specific parts of the field.
Precisely. This particular study aimed to map the spatial distribution of chlorophyll level and yield maps for fields under corn, ZMAs, and wheat, Triticum aestivum. They related these maps to different quantities of nitrogen and temperature fertilizer application. The chlorophyll gauge was monitoring to stress level for management, essentially using chlorophyll as an indicator of plant health and nutrient needs.
What kind of methods did they use to gather this data? They used a combination of methods, things like multispectral Landsat, satellite imagery, hyperspectral reflectance readings from a handheld spectrophotometer, and the ProSales simulation soil model, which takes soil factors into account. They measured key indicators like leaf chlorophyll content, LCC, and LAI leaf area index, which relates to the density of leaves.
Okay, another agricultural application, predicting seasonal rainfall and crop production using machine learning. Why is this so vital, especially in regions heavily dependent on rainfall?
This is critically important because, as the paper notes, agricultural growth in many regions, like India, is going downwards, partly because it's so heavily dependent on unpredictable rainfall patterns.
Right, the monsoon lottery.
Exactly. This unpredictability leads to farmers facing significant losses if the rains fail or come at the wrong time. The core need is for prior information, accurate predictions of rainfall and crop yield. This would allow farmers to plan their cultivation cycles much more effectively for both the Kharif, monsoon, and Rabi winter seasons, optimizing resource use and minimizing the risk. The goal is to use machine learning scientific and statistical methods to provide these crucial forecasts.
Which machine learning regression models did they explore for this prediction task? And what were the key findings from their comparison? Did one model work best for everything?
No, interestingly, they compared several different machine learning regression models: linear regression, Bayesian linear regression, decision forest regression, Poisson regression, and boosted decision tree regression.
Go.
The comparative results revealed distinct strengths depending on the task. For rainfall prediction, they found that the linear regression and Bayesian linear regression models comparatively produced the best result in terms of accuracy. Simpler models worked well there.
But for crop prediction?
For crop prediction, however, the boosted decision tree regression model is achieving the better result across various evaluation metrics like RMSE, RAE, RSE, and coefficient of determination. This suggests its superior ability to capture the more complex factors influencing crop yield reliably, different models for different related tasks.
Interesting. Now let's shift gears again to enhancing cybersecurity and digital reliability. The Internet of Things, IoT, presents enormous opportunities for connectivity, but also, as we know, significant security concerns. What are some of these pervasive risks that arise as more and more devices get connected?
Right, the IoT revolution. It anticipates billions of associated gadgets connecting to the internet. But unfortunately, this introduces various protection and security worries for the last customers. It's a huge attack
What
surface.
kind of worries?
They're broad, encompassing critical threats like identity and information burglary, unauthorized gadget control. Imagine someone hijacking your smart thermostat or security camera, information manipulations, malicious network server alterations, and the ensuing impact on application stages. Basically, any smart device connected to the internet, from your fridge to industrial sensors, can become a potential vulnerability.
I recall seeing some alarming statistics mentioned about escalating malware attacks targeting IoT devices. What do the reports show about the scale of this threat? Is it getting worse?
It seems so, yes. The scale of the threat is alarming. Reports like the SonicWall investigations mentioned in the paper show that IoT malware attacks absolutely skyrocketed. They apparently bounced 215.7% till 32.8 million out of 2018.
Wow, tripled in a year.
Nearly tripled, yeah. And in early 2019, they continued to surge, outpacing the initial two-fourths of 2018 by much above 55%. This data clearly indicates that the threat landscape for IoT is growing exponentially and becoming increasingly sophisticated. The attackers are definitely targeting these devices.
How does the study categorize these IoT threats? Based on risk level, perhaps?
Yes, it categorizes them into 4 distinct attack levels based on their potential impact. Level 1, low, involves passively breaching data confidentiality, things like simple eavesdropping or traffic analysis. Level 2, medium, includes active alteration and eavesdropping, such as man-in-the-middle attacks where communications are intercepted and potentially modified.
Okay.
Level 3, high, is about impersonation for unauthorized access, spoofing legitimate devices or cloning their identities, leading to privacy disclosure or service interruption. And level 4, extremely high, involves direct, severe attacks on systems, taking unauthorized access, making systems inaccessible, launching a denial of service attacks, maybe through bulk messages or system jamming, really disruptive stuff.
And what are some of the proposed technical solutions or countermeasures for these increasing IoT threats? How do we fight back?
The paper suggests specific technical countermeasures tailored to different threat types. For confidentiality breaches, like eavesdropping, they recommend symmetric encryption techniques. To combat impersonation, identity-based authentication protocols are crucial. For cloning attacks, they propose using physically unclonable function, or PUF technologies. These embed unique, uncopyable physical properties into the device hardware itself.
Like a fingerprint for the chip.
Kind of, yeah.
Mm.
For privacy, anonymous data transmission methods are vital, and robust authorization mechanisms are key to preventing interruption attacks and unauthorized access. So it's really a multi-layered defense strategy that's needed.
Okay, another persistent digital threat, particularly in web applications, cross-site scripting, or XSS vulnerabilities. What exactly is XSS, and why has it remained such a widespread problem for so long? It feels like it's been around forever.
It practically has. XSS is identified as the most commonly exploited flaw in today's web pages. It's designed to compromise the confidentiality or integrity of user data or systems interacting with a vulnerable website. And yes, it has been around for a long time, and the amount of cyber attacks, including XSS, has grown exponentially since the internet's early days. It's persistent because it exploits a fundamental interaction between a user's browser and a vulnerable website, how websites handle user-supplied input.
How does the XSS attack mechanism typically work? Why is it so insidious?
It works by an attacker injecting malicious code, usually JavaScript, into a legitimate website. This might be through a comment form, a search box, a URL parameter, anywhere the site accepts user input and doesn't properly sanitize it. This injected code is then triggered to receive a response when another unsuspecting user's browser loads the compromised page or interacts with the malicious content. The vector for injection is carefully crafted by the attacker to bypass any restrictions imposed by various aspects of a web page, like input filters or basic web application firewalls, WFs. Once injected, this malicious code runs within the victim's browser, but under the security context of the legitimate website.
Ah, so the browser thinks the malicious code is part of the trusted site.
Exactly. That's the insidious part. This allows the code to potentially steal the user's cookies, session tokens, which keep them logged in, hijack their account, redirect them to phishing sites, or even perform actions on the website on their behalf without their knowledge.
And why aren't traditional client-side defenses, like filtering input in the browser, sufficient to prevent these attacks?
The paper explicitly states that client-side input filtering and validation are not enough to prevent attacks. It cites the infamous Sammy computer worm from back in 2005. This worm spread on MySpace and shut it down within 20H, purely by self-replicating via a clever XSS vulnerability that bypassed MySpace's filters.
Wow, shut down MySpace in less than a day.
Yeah, this historic example demonstrates that even seemingly robust client-side defenses can often be circumvented by determined and clever attackers. It really necessitates strong server-side validation and output encoding, plus more sophisticated application-level security measures. You can't just rely on the browser.
What were some of the crucial real-world insights gained from testing popular web applications for XSS vulnerabilities in this study? Did they find surprising gaps even in big sites?
They did. The testing revealed several eye-opening findings. For example, they found that certain popular sites actually allow for certain HTML tags to be passed through the way, tags like MNG, SVG, or even marquee, which can potentially be exploited for XSS attacks if not handled carefully. Also, while WAMPs are able to detect event handlers in their primitive state, things like onerror or onload used to trigger JavaScript more sophisticated or encoded attacks can still bypass these detections. A particularly concerning discovery was that the username and password of a user were found stored insecurely within HTTP request responses, a VTOP, likely Valor Institute of Technology's online portal, highlighting a significant potential security oversight.
Ouch. Usernames and passwords in requests. Not good.
It's definitely not. They also noted that modern web frameworks aren't immune. Angular-based applications, like the example given of Big Basket, have their own specific types of XSS vulnerabilities that require specialized knowledge to find and exploit. It shows that vigilance is needed across all platforms and technologies.
Okay, shifting to network security. Anomaly detection is absolutely key for spotting intrusions, right? Catching the unusual activity. How is an ensemble of machine learning models being used to improve this detection, especially given how complex network traffic data is?
Right. The challenge for intrusion detection systems, IDS, is immense precisely because raw network traffic contains a large number of attributes that add to the complexity of the model. There's just so much data, and much of it is normal. To overcome the limitations of using just a single machine learning model, the proposed method uses an ensemble approach on classifiers.
Ensemble again, combining models.
Exactly, combining multiple individual models to create a more robust and accurate detector. The idea is that the collective wisdom is better than any single model.
And how is this ensemble configured? How does it work in practice to enhance detection accuracy?
It's designed as a stacked ensemble. The outputs, predictions, from 3 individual classifiers specifically, decision tree, DT, logistic regression, LR, and support vector machine, SVM, are not the final answer. Instead, these outputs are fed as new input features into a final random forest RF ensemble classifier.
So the random forest learns from the predictions of the other 3.
Precisely. This allows the random forest to learn from the strengths and weaknesses of the other models, effectively weighing their opinions and making a more informed and accurate final decision on whether a particular piece of network traffic is anomalous or potentially malicious.
Data preprocessing seems to be consistently highlighted across these studies as absolutely critical. What specific steps are crucial here for anomaly detection, especially when dealing with messy, raw network data?
It is indeed absolutely critical. Often, good preprocessing is more impactful than the specific model choice itself. For anomaly detection with network data, they detail several crucial preprocessing steps. This includes handling redundant and irrelevant data and addressing the common problem of class imbalance, where normal traffic vastly outweighs malicious traffic, making it hard for models to learn the rare cases.
Right. How do they handle missing data?
Importantly, they prefer replacing null values or missing values, using statistical measures like the mean, mode, and median of the column, rather than simply deleting rows with missing data. This helps avoid data loss, which can be significant in large data sets.
Okay. And categorical data, like protocol types.
For categorical data like TCP, UDP, ICMP, they use one-hot encoding. This creates new binary columns for each category, e.g. ISTCP, ISUDP, and is generally preferred over simple label encoding, assigning numbers 1, 2, 3, because it avoids implying an arbitrary numerical order or priority between categories that don't exist.
Makes sense. Anything else?
Yes. Feature scaling is vital. Using techniques like min-max normalization, scaling values to be between 0 and 1, or standardization, scaling to have 0 mean and unit variance, this prevents columns with naturally larger numerical ranges, like packet sizes, from unfairly dominating the model's learning process compared to columns with smaller ranges.
Right, putting everything on a level playing field.
Exactly. And crucially, they performed feature selection, removing nearly 7 columns attributes like flow ID, source IP port, destination IP port, protocol, and timestamp.
Why remove those? They sound important.
They argue that these attributes do not contribute to the performance of the model for detecting the nature of the traffic, benign versus attack, and worse, they can be used by the intruder. For example, specific IPs or timestamps might fingerprint the dataset or be easily spoofed, potentially misleading the IDS. So they focused on features describing the traffic behavior.
Ah, okay. That makes sense. And the performance of this carefully pre-processed ensemble model for anomaly detection, how did it stack up against the individual models?
The results were truly significant. The ensemble model achieved an impressive accuracy of 98.44%, precision 100%, recall 96.88%, and F-score 98.42%.
Wow, 100% precision.
According to their results, yes, meaning when it flagged something as an anomaly, it was correct. And this overall performance clearly outperformed the individual models by a substantial margin. For instance, SVM alone achieved about 94.4% accuracy, and decision tree was much lower at around 72.2%. This really demonstrates the power of combining different machine learning strengths along with meticulous preprocessing to create a highly effective and reliable intrusion detection system.
Okay, one more in this section. E-commerce, but with a twist. Using blockchain for a distributed site called Sanskriti. What problems with traditional e-commerce does this aim to solve?
Right, this tackles some common criticisms of traditional centralized e-commerce platforms. Things like potential monopoly power held by the platform owner, the difficulty for small businesses to register or advertise fairly, and significant security and privacy issues related to how customer data is stored and managed centrally.
So the idea is decentralization using blockchain.
Exactly. Sanskriti is proposed as a decentralized e-commerce platform utilizing blockchain technology to address these issues.
What are the key features enabled by blockchain in this context?
Several key features stand out. First, direct peer-to-peer interaction. Buyers and sellers are connected without the participation of middlemen, reducing platform fees and control. Second, smart contracts. These are described as a set of rules that parties in a smart contract agree to follow, automating aspects of the transaction like payment release upon confirmed delivery, potentially reducing formality and expense associated with traditional approaches.
Okay, what else?
They also mention a fast KYC, Know Your Customer system, claiming it can be completed in simple and easy steps and can be done from any convenient place, perhaps leveraging decentralized identity concepts. A really unique feature is their hybrid data storage approach.
Hybrid, not all on the blockchain.
Right. Data is stored in parts into MongoDB server and blockchain. They argue this approach helps reduce the cost of writing all data on blockchain, which can be expensive, and also improves user privacy because an attacker breaching one system would only get some and irrelevant data which cannot be decoded without access to the other part.
Interesting trade-off. How about security?
They claim enhanced security by linking the wallet I to the login security. This means a hacker would need not only a UID and password, but also needs to crack or get hold of the wallet to enter our application, adding another layer of authentication. And finally, transparency. They note that whenever any action takes place, such as this listing of product, the contract needs to be signed and the gas, validator's fee, and these transaction details are written on the chain for transparency. Anyone can verify the actions.
Okay, one final technical deep dive comparison. Cache replacement strategies in content-centric networking, CCN. This sounds fundamental to network performance. What's the core idea?
Right. This paper focuses on the quality of experience, or QoE, for internet users. Customer satisfaction has been a prime concern, and delivering good QoE is the primary goal of any internet service provider.
Makes sense. Faster loading, smoother streaming.
Exactly. The paper introduces content-centric networking, CCN, as a rising new architecture which paves way for a looming internet. It's fundamentally different from the current IP-based architecture. CCN accentuates the data by making it directly addressed and routed, rather than addressing specific host machines. You request content by name, not by server location.
How does CCN improve QoE?
One key way is through in-network caching. In CCN, several copies of the same data are stored in the network on routers along the path. This means any node can serve future requests for that content if it has a cached copy. This significantly reduces the network load and bottleneck on the original server and gets the content to users faster from a nearby cache.
But caches are limited in size, right? That brings us to the replacement problem.
Precisely. Due to limited CS size, content store, the cache on each node, strategies are needed to replace the content in CS whenever the CS is full and when a new request arrives. You have to decide which existing piece of content to kick out to make room for the new one.
And what strategies did they compare?
They analyzed several common ones: LRU, least recently used; LFU, least frequently used; random cache replacement and semantic cache replacement strategies. They compared these across various underlying caching strategies like LCE, LCD, prop cache, magic, different ways nodes decide whether to cache something in the first place, and across different cache sizes.
What were the key findings from this comparison? Which replacement strategy works best?
It's not one size fits all. They evaluated performance based on the cache hit ratio. A higher ratio means more requests were served from the cache, which implies reduced load on server and maximum efficiency, ensuing in less delay in transmission. They found that the classic LRU replacement strategy has higher performance with regard to less consumption of bandwidth and better throughput in many scenarios. However, random cache works efficiently with prob cache caching as cache size increases. Their overall conclusion was that likely a combination of replacement strategies would be effective for all cache sizes and caching strategies, suggesting adaptive or hybrid approaches might be optimal in real-world CCN deployments. This raises an important question. What truly powers these incredibly diverse applications across so many domains? It's the computational powerhouse of the techniques themselves, really. The underlying algorithms.
Right. So after that incredible tour of applications, let's maybe talk about the common threads, the core machine learning and deep learning algorithms that make all this possible. Convolutional neural networks, CNN, they seem to be everywhere, especially in image processing.
Indeed. CNNs are truly the visionary architects behind almost all the image-based applications we discussed. We saw them in action from OPG analysis and dentistry.
Right, the dental x-rays.
So kidney stone classification, self-driving cars perceiving objects, brain tumor detection, even things not detailed as much here like flower animal classification or plant disease ID mentioned in the proceedings. They are absolutely foundational because they excel at understanding visual information.
How do they actually work? How do they see and interpret images so effectively?
Their core function is extracting picture features pixel by pixel, but in a hierarchical way. They do this through a specific sequence of layers. Primarily, you have convolutional layers, which imply filters like little magnifying glasses to detect patterns like edges, corners, textures.
Okay.
Then pooling layers, which reduce the spatial dimensions of the data, kind of summarizing regions while retaining the most important information. And finally, fully connected layers at the end, which take all those learned features and perform the classification task, like deciding, is this a cat or a dog? Or is this tumor benign or malignant?
So it builds up understanding layer by layer.
Exactly. This layered approach allows them to process the data in a simple way, breaking down complexity without losing any feature that's important. This makes them exceptionally adept at managing huge data sets and identifying intricate patterns in images that humans might miss. And as we saw, you get variations like ResNets and XResNets, specifically tailored for medical imaging challenges, or MobileNet designed for efficiency on, say, mobile devices.
Okay. Tree-based algorithms also showed up in many places: diabetes prediction, crop production, toxic comment classification. What's their core role as decision makers?
Their versatility is truly impressive. We saw them used in very diverse predictive tasks. Diabetes prediction, yes, but also things like predicting landslide susceptibility, forecasting crop yields, detecting network anomalies, classifying toxic comments, even predicting EV purchase willingness, another paper in the volume.
So very flexible.
Very flexible. Decision trees form the foundational unit, asking a series of yes-no questions based on features. But their real power often comes from ensemble methods built upon them.
Ensembles again.
Ensembles again. For example, random forest accumulates many classification and regression trees, hundreds or thousands sometimes, and combines their individual outputs, often by averaging or voting, for more robust and accurate predictions. It reduces the risk of relying on one potentially flawed tree.
And gradient boosting, they came up too.
Right. Gradient boosting, including XGBoost, which we discussed, adds several improvements that significantly enhance the performance and accuracy of the model. Boosting, in particular, optimizes using a sequential and iterative process. New decision trees are added in each iteration, specifically designed to correct the errors made by the trees that came before it. It steadily learns from mistakes, reducing loss and error, leading to highly accurate models, often state-of-the-art for structured data problems.
Okay. And support vector machines, SVMs, you call them the margin maximizers.
Yeah.
Where do they fit into this algorithmic toolkit?
SVMs are widely applied across classification problems. We saw them mentioned for diabetes prediction, anomaly detection, animal classification, even EEG analysis for Alzheimer's. Their key principle for classification is geometric. They construct hyperplanes, basically, decision boundaries in a high-dimensional feature space.
High-dimensional space. Sounds complex.
It can be, but the goal is simple. Maximize the margin, or the distance, between this hyperplane and the nearest data points of every class. They try to find the clearest possible separation line or plane between the different categories in the data.
What are their advantages?
A notable advantage is their effectiveness on small data sets, and also works well with high-dimensional spaces where you have many features. Plus, they have mechanisms that allow them to easily ignore the outliers, making them quite robust to noisy data points that might throw off other algorithms.
We also heard about clustering algorithms like k-means or fuzzy c-means used for grouping things. Where are they applied?
Clustering plays an essential role in unsupervised learning finding patterns without predefined labels. We saw it mentioned in the context of customer understanding, like for smartphone market research, or the knowing your customer's motivator analysis.
Right, and finding groups of similar customers.
Exactly. Clustering algorithms break up data into quite a number of clusters based on the resemblance of features found in the images or data points. They group similar items together automatically. K-means is a very popular method, but the proceedings also mention advanced forms like repetitive median-based K-means, RMK-means, which can sometimes be more effective, especially with outliers.
Okay. And we also encountered neural networks beyond just vision, learning from sequence and complexity. Specifically, recurrent neural networks, RNNs, and long short-term memory, LSTMs. Where do they shine?
These are crucial for sequential data processing, where the order of information matters deeply. We saw them in applications like the transformer models for question answering and text generation, in customer call analysis, where the flow of conversation is key, and even mentioned for things like unusual event detection from surveillance videos.
How do they handle sequences?
RNNs are designed with internal memory loops, allowing them to recall the input from previous steps in the sequence, giving them context over time. LSTMs are a specialized, more powerful type of RNN capable of learning order dependence in sequence prediction problems. They are particularly good at handling long-term dependencies, relationships between elements far apart in the sequence, making them very effective with time series data like speech, text, or financial transactions.
And you also mentioned radial basis functional networks, RBFNs.
Yes, briefly. They were noted for their role in complex nonlinear problems, like the example of energy efficiency enhancement of wind power plants. They are valued for features like good generalization, online learning ability, strong tolerance to input noise, and easy design, making them suitable for certain engineering control problems.
Finally, Bayesian networks came up for reasoning under uncertainty.
Right. Bayesian networks are a type of probabilistic graphical model. They were mentioned in the context of predicting software requirement complexity.
Software complexity, that sounds objective.
It often is. And that's where Bayesian networks are useful. They excel in uncertain situations. They provide a way to combine historical project data and expert opinion within a probabilistic framework. They also allow for what-if analysis to analyze the impact of changes in some nodes on the other nodes in the network. And importantly, they can use ordinal measures to handle subjective judgments effectively.
That's a comprehensive toolkit of algorithms. But as you said, a common thread we've seen across almost all these papers is the absolutely critical role of data preprocessing and feature engineering. It seems like it's a universal necessity before any of these powerful algorithms can even get to work effectively.
It truly is. You really can't overstate its importance. Almost every single research paper highlights data preprocessing as an integral first step. Sometimes it's acknowledged as being 80% of the actual work in a machine learning project.
80%.
Easily. It's fundamentally about altering or encoding data to make it easier for the machine to parse it. Ensuring the data is in the right format, free of errors or inconsistencies, and optimized for the specific algorithms you plan to use so they can learn effectively. Without proper pre-processing, even the most advanced, sophisticated models can fail miserably. Garbage in, garbage out, as they say.
What are some of the most common techniques researchers apply during this crucial pre-process stage? We touched on some already.
Yeah, there's a wide array of standard techniques that reappear constantly. Cleaning is fundamental. That involves steps like normalization, scaling data, tokenization, breaking text into words, stop words removal, getting rid of common words like the, a, is, and stemming, or lemmatization, reducing words to their root form, as we saw in the Assimi's text summarization example. It also includes removing noise or handling missing information in data sets, which came up in anomaly detection and diabetes prediction.
Right, dealing with messy data.
Exactly. Handling missing values is often done carefully using imputation methods like replacing missing values with the mean, mode, and median of the column, rather than just deleting rows to avoid potentially significant data loss. For categorical data encoding like colors, product types, network protocols, one-hot encoding is frequently preferred over simple label encoding, assigning numbers 1, 2, 3. This avoids implying a false numerical priority or order between categories that the model might misinterpret. And feature scaling, using techniques like min-max normalization, scaling to 0-1 range, or standardization, scaling to 0 mean unit variance, is crucial, as we discussed, for anomaly detection. It ensures that no single data column with naturally larger values dominates the model's calculations or distance metrics unfairly, puts everything on an equal footing.
And then there's feature selection, which also seems vital. What impact does that have on the model's performance and efficiency? Choosing the right features.
Feature selection is vital. It's the process of identifying the most important features within a potentially vast data set and discarding the irrelevant or redundant ones. This helps to reduce the dimensionality of the problem. By focusing the model's attention on only the most relevant data points, models can become simpler, faster to train, less prone to overfitting, and often, counterintuitively, more accurate because they are less distracted by irrelevant noise in the data.
Any examples of selection methods mentioned?
Yes, the proceedings mentioned using statistical tests like Pearson's correlation coefficient, used for vaccination prediction in one paper, or information theoretic measures like infogain attribute eval, used for diabetes prediction, to objectively rank and select the most influential variables for the prediction task.
Clearly, these advanced methods are powerful, but they don't come without computational challenges. The outline mentioned the high demand of deep learning specifically.
Yes, that's a significant practical hurdle. CNN algorithms, for instance, require a lot of mathematical convolutional computations. These operations, repeated across large data sets and deep networks, take a lot of time and has high computational demand. This can make training these models very resource-intensive, requiring specialized hardware and significant time. Deploying them efficiently can also be a challenge.
So how are researchers addressing these computational challenges, both through hardware innovation and maybe smarter algorithm choices?
They're tackling it on multiple fronts, definitely. On the hardware side, the use of GPU computing, graphics processing units, is now standard. GPUs can be used for accelerating image processing and other deep learning tasks because their architecture is highly suited to the parallel matrix operations involved, offering significant speedups over traditional CPUs.
Okay, so specialized hardware helps.
Massively. Researchers can also leverage software techniques to parallelize CPU cores to process images faster, for instance, using libraries like Ray in Python, mentioned for flower classification, to distribute the computational workload across multiple processor cores or even multiple machines.
And algorithmically.
From an algorithmic perspective, the choice of model architecture matters. As we saw, algorithms like YOLO or faster RCNN are sometimes selected precisely for their favorable speed versus accuracy trade-off and computational efficiency. Some models, like the original YOLO, were even designed specifically to be able to run on systems with no GPU, making them more accessible for deployment on less powerful devices or in resource-constrained environments. There's a constant push for more efficient architectures like MobileNets or BERT.
It also seems like this is a continuous iteration cycle of research. It's not like these problems are static or solved. So many papers mention future work.
That's a crucial point to take away. These fields, data engineering, machine learning, AI, are incredibly dynamic. They are not static disciplines where problems are simply solved and then researchers move on. Far from it. The fact that so many papers conclude with sections on further works or future scope is a clear indicator of the continuous, evolving nature of the research. Each breakthrough, each new technique, opens up new questions and new avenues for exploration.
Can you give us a few examples of where future work is currently focused based on these proceedings? What's next?
Certainly. Just pulling a few examples mentioned. For cyberbullying detection, a future direction is building a system which will detect cyberbullying content on image data, moving beyond just text analysis to understand harmful visual content like memes. In network anomaly detection, a key focus is on implementing real-time network data in deep learning models to catch sophisticated threats as they happen, rather than just analyzing logs after the fact. For the software requirement complexity prediction using Bayesian networks, researchers aim to work on a larger data set to test the efficiency of the model, validating their approach more rigorously. For currency detection for visually impaired users, they noted the need for improving the pre-processing drastically to handle worn-out or damaged notes better. And for self-driving cars, integrating a lane departure warning system was cited as a logical next step to enhance safety features. This consistent forward-looking perspective truly demonstrates how the field is constantly building upon previous advancements and tackling new challenges.
So after this whirlwind tour through the cutting edge of computational methods and data engineering, what's the big takeaway for you summarizing all this? Hashtag tag check outro.
What really stands out to me is the sheer breadth and, maybe more importantly, the interconnectedness of all these applications. It's quite stunning. We've seen computational methods transforming everything from highly precise medical diagnoses and enhancing public safety with smarter infrastructure to optimizing agriculture in the face of climate change and building more resilient, secure digital infrastructure.
It's everywhere.
It really is. It's a powerful testament, I think, to how foundational data engineering and computational intelligence have become across virtually every sector of our modern lives. They're not niche anymore. They're core.
Exactly. And this deep dive, well, it has aimed to be your shortcut through that complexity, equipping you, our listener, with a foundational understanding of these sometimes intricate topics. We really hope it's delivered those aha moments, highlighting the surprising facts and connections that link these advanced technologies to our daily lives, and showing the immense potential they hold for the future.
As we conclude, maybe leave you with a thought to ponder. We've witnessed how these computational methods are not merely solving existing problems. They are fundamentally redefining what's possible. They're transforming human experience, often in ways we're just beginning to grasp, even at this college level of understanding we aimed for.
Right.
So, as these incredibly adaptable tools become even more sophisticated, even more ubiquitous, what ethical responsibilities do we have in designing and deploying them fairly and safely? And looking ahead, thinking creatively, what previously unimaginable challenges might you foresee these powerful methods tackling next? What's just over the horizon?